Good morning, everyone. We have seen the usage of the Numpy universal functions. Let us continue to see few more universal functions of Numpy to find or to compute the statistics of an array. Numpy is a powerful library for numerical computation in Python, and it provides functionalities for working with arrays, matrices, and various mathematical operations. Numpy universal functions are efficient functions that operate element-wise on Numpy arrays. This we have already seen in the session 4. They are essential for numerical computations and allow for fast executions of operations. And let us see once again the difference between the natural Python functions and the Numpy universal functions. See, basically the natural functions comes with a Numpy, comes with a Python, generally not designed for element-wise operations in a sequence, whereas the Numpy universal functions are designed specially for performing operations on an arrays element-wise. Coming to the performance of universal functions, they are faster when compared to natural functions. These natural functions are a bit slow when applied on a huge data, because they lack vectorization of values. Whereas universal functions, particularly the Numpy universal functions, are highly optimized for performance, especially when we deal with the large arrays. Of course, the syntax often requires looping constructs or list comprehensions in natural functions, whereas it is very concise and there is a provision to directly operate on numerical arrays in universal functions. In natural functions, there is a limit on applying different operations on different dimensional sequences, whereas in Numpy, irrespective of the dimensions, you can apply different operations with the help of broadcasting. Broadcasting is one of the greatest feature of Numpy that aligns the array's dimensions before applying any operation. We'll see this broadcasting concept in next session. Coming to the available functions, there's a limited range of mathematical functions available, comes default with the Python, whereas when you import Numpy package, you get a wide range of mathematical, statistical, and trigonometric functions. In addition to it, if you use Sci-Fi library, there are a huge number of mathematical and statistical functions under stats module. For example, the natural functions of Python includes mapping, sum, minimum, max, absolute, like that, without any successor or producer, library, signature. Whereas in Numpy, you can just start with the Numpy, signature NP, dot the universal function. There are so many functions available, and equivalent functions are, for sum it's np.sum, for min it's np.min, for max it is np.max, for absolute it is np.absolute. As I told you, the natural functions are bit low because of the loops, whereas the universal functions are quite faster because they run on the compiled codes. These natural functions commonly applied on scalar values or the sequence of data, whereas the Numpy arrays supports arrays operations on huge data. In natural functions, no need to support for vectorized operations, whereas in universal functions, a Numpy fully supports vectorized operations and helps us to enhance the performance. These are the basic differences between the natural Python functions and Numpy universal functions. Let us see the simple universal functions that are used to find the aggregation of array elements. To find the minimum of an array, if an array is of 1, 8, 2, 5, 7, 3, and 10 elements, and out of which, if you wanted to find the minimum using universal function, you can simply use np.min of data. Of course, you can also directly see the min of it. Print min of data, print max of data. You see there is no difference, but if you wanted to see how it is performed, we have already seen time it will gives us the time taken to compute the code snippet. See, you don't see the much difference when you are working on a smaller collection, but definitely you can see the greater performance variation when you apply on huge data. Right now you can observe the time taken by the natural function and the universal function. Okay. Now you can see the standard deviation is very less, right? So this is the biggest difference. Now we can also see certain aggregate operations on arrays or summing of the elements and finding the product. You can simply use np.sum on array data and then np.product ROD on a data and then mean. So these are the basic aggregate functions. And not only this, we can also find the cumulative sum and then cumulative products of an array using universal function cumulative sum and then cumulative product. So now you can see the cumulative values. If you just print the data, you can easily get the difference. Now 1 plus it is 9, 9 plus 2 11, plus 5 is 16, plus 7 is 23, plus 3 26, plus 10 is 36. That's what is cumulative sum. Cumulative product 1 into right? 1 into 8 is 8, 8 into 2 is 16, 16 into 5 is 8, 80, sorry, 80, 80 into 7 is 560, 560 into 3 is 1680, 1680 into 10 is 16,800. So like that, you can also simply compute the cumulative sum and cumulative product. Now, so far we have seen the aggregate operations on a single dimensional array. But the greatest advantage of Numpy is you can apply these universal functions on any dimension. That's what I told you. It helps us through broadcasting. We will discuss the broadcasting in the next session. But simply you can directly get a result. See, simply to get the sum of an array, you can simply use a natural sum, but whereas it gives the sum of the elements, it's a column wise. You can always pass access. If I provide access is equal to 0. Now, let us see what is the error. It is an invalid argument for sum. Okay, so since I am using a natural sum, it's not possible, but you have always a provision to provide the access that you wanted to calculate the sum or the product or any other operation in Numpy. So np dot sum of array. Now you can see when I pass 0, it sums across the columns. If I give 1, then it finds the sum row wise. I mean to say column wise, the first row and then all the columns. Second row, all the columns. So first row, I mean first column wise, and a first row is 1 plus 2 plus 3 is 6. And the column wise, second row is 4 plus 5, 9 plus 6 is 15. And then third one is anyhow 24. Hope you got the difference between these two. 0 indicates what? Row wise operation. And then column indicates, 1 indicates column wise operation. Let us see the complete information about this array. Now you can see it is, you can simply use info, np.info to get the information of an array. And it's a 2-dimensional array with the shape 3 into 3. And then total bytes are 12 and 4. And then item size, each item is of size 4 bytes. And it's aligned. That's what you are able to see in the matrix format. And then, of course, the elements will be in a continuous way, right? So these are the other features of an array. So the type, all the elements in this array are of integer 32, each of 4 bytes length. Now let us see, simply you can get the minimum and maximum of arrays using np.min and np.max. You also have an alternate way of using the name of object, array object is an arr.min. So both are same. So these both are same. You can replaceably use it, right? And to find the maximum, you have np.max. And coming to the basics of statistics using Numpy. And basically, we wanted to find the characteristics of the data using statistics. What are the characteristics? Let me call it as a population. What is population? Population is a complete collection. Everyone. Okay, that's what we call it as a universal collection. Right? So on a population, you can find the characteristics. What are the characteristics of population? They are mean, standard deviation, and variance, etc. Okay, we usually represent them with the mu is to represent the mean or the central tendency, and standard deviation is a sigma. Okay, similarly, we'll also apply on sample data. What is sample data? In this case, population is called as a array, whereas the sample data is a part of an array, right? We call it a sub-array in our case. So part of population. You have so many methods to collect the samples, right? Random samples, equisamples, clustered samples, the distributed samples, like that. You have so many methods. So you also have a similar characteristics of the subarray or the sample, like the same central tendency, standard deviation, variance, and you'll also see how it is behaving on par with other elements, right? Now coming to the central tendency, we find the central tendency with three characteristics. They're called mean, median, and mode. Mean means the average value of a set of numbers. The median means the middle value of set of numbers when they are ordered. Particularly when you find the median, if the collection set of values are the total set of values are odd, then it's exactly the center value. And if they are even, it is an average of the middle two values. Whereas mode in represents the most frequent element of a collection. Now we have as simple direct methods to find these characteristics of the data, such as mean, median. Directly you can use np.mean of print array. I will understand this is what is an average of an array. Similarly, you can see the median. So since there are 9 and it's the fifth element, since there are 9 elements in the array and middle element after order is 5, right? So coming to the mode, so we cannot directly find the mode from Numpy, but we need to use a sci-fi library and the stats module to measure the mode from a collection. We will discuss in detail about this scientific Python library for more statistical operations. But as of now, to measure the mode, you need to write a bit lines of code. So mode of elements are called the most frequent element in the collection. You need to import sci-fi library, and then now you have your array, right? And since in the previous array I don't have any repeated values, that's what I have taken a new example, all right, with some repetition, and then it's stats mode. You observe my array is of 3 into 4 shape array. Now you can see my array elements are having the highest frequency. So one is occurred 3 times, and then 2 occurred 2 times, 4 occurred 2 times, and then 7 occurred 2 times, and then 3 is the most frequent value, where 3 can be treated as a mode value of this data collection or an array. Now let us see the standard deviation and variance. I don't want to go in detail about the mathematics behind the standard deviation and variance, but let's have a simple understanding of what is a standard deviation and what is a variance. We know the variance is a simple measure of dispersion of data in the collection, right? I mean to say variance will let us understand how an element is far from its central tendency value. If you have a mean, and then variance of any element is the distance between that element and the mean value. Whereas standard deviation is a square root of the variance. It indicates how much the data deviates from the mean. Okay, there's a slight difference, right? So let us see the standard deviation using a universal function STD. So now this is the standard deviation of a given array, and then variance also you can simply find using np.var function straight away. As we know, the behavior of the data can be measured by using a different statistical techniques. So particularly inferential statistics, whereas when a graph is generated, you can easily find where the data is spread and skewed. The skewness and spread of data can be measured by using interquartile range. To find the interquartile range, so one of the characteristics of a data, you can use percentile calculation on top of different quartiles. Our data is divided into 4 equal regions. The first 25% of data is treated as a quartile 1. Second 25% up to 50% is treated as a second quartile, and up to third quarter up to 75% of the data is treated as a third quartile, and whereas the 100% at the 100% it is treated as a fourth quartile, where when the data is normally distributed, most of the data lies between first quartile to third quartile. I mean, from 25th percentile to 75th percentile. That's where interquartile range is always measured as a spread of data between first quartile to third quartile. A simple formula to find the interquartile range is equal to Q3 minus Q1. So to find the percentile, you have a percentile universal function in Numpy. npd.percentile is a given an array, and the first 25% is stored into Q1, and then up to 75. Because I'm straight away calculating Q3 because I wanted to find interquartile range where the data is spread. So this 50%, okay, this 50% is key where maximum data is spread. You can find np.percentile array up to 75%, and then interquartile range is equal to Q3 minus Q1. And you can simply see the interquartile range is 4. Okay. Let's continue and then see a few examples how to compute aggregations on an array using universal functions. Of course, we have covered maximum, but let us also see a few more examples and then a major difference between the natural aggregate functions and then universal aggregate functions. under Numpy library. Often when we face with a large amount of data, the first step is to compute summary statistics for the data in question. What's mean by summary? You said minimum, maximum, okay, mean, mode, median, standard deviation, interquartile ranges. So all these are called as summary of a data, right? Now you can see, so this is the data in points that I have randomly generated using random function, and simple sum works like, see, whereas you'll have a loop basically, so that navigate to every element of a collection and then finally finds the sum. Now you can see the difference. This we have already seen, but for a easy understanding, I am trying to portray how the natural sum and then universal function sum in Numpy are performing. Okay. Now, as you know, we have already seen maximum about it. Then so you can also apply not only on single dimensional array, as I told you, you can apply on multi-dimensional arrays. So we call them as a multi-dimensional aggregates. When you perform multi-dimensional aggregates, you have to be very careful because not all the operations can be just performed when the dimensions are different. Okay, so that's what the normal functions doesn't support any operation between different dimensional sequences, whereas in Numpy they do. This we have already covered the previous slide. Whereas let us see, there are two more operations. One is augment and then argmax. Augment returns the index position of the minimum element in the collection. Okay, and this collection, the minimum element. What is the minimum element? Is 0.1164 and so on. This is what, and then the corresponding index position 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Okay, so this is the 9th location. So that's what it returns, the index position of the minimum value of an array through argument. Similarly, argmax. Argmax is one of the universal functions of an Numpy, which returns the index position of the maximum value of an array. Right? Now you can see what is the maximum value in it. If you want, you can see the maximum value. How to find maximum value? M dot max of, right? Now you can see, you can just print it now. So this is the maximum value. Where does it locate? 0, 1, 2. So here, right? In third position. So argmax returns the index of the maximum value of an array, right? Now, these are the few more functions available, right? So Numpy provides many other aggregate functions, but we don't discuss them in detail here. Okay, so apart from the universal functions for aggregation on an n-dimensional array, we also have a not a number safe counterpart that computes the results while ignoring missing values, which are marked by this special IEEE floating point NAN. Is one of the important thing we all need to remember, because when you are dealing with the data, so when you are finding the summarization, that's what is some minimum, maximum and all, you cannot consider the empty locations or the cells where you don't have a data. Because if no data is treated as a minimum value, then there is no meaning. So, and when you're taking average also, you cannot take them as counts. So for which there is a standard counterpart offered by the IEEE as a floating point NAN. So irrespective of the the operations that you are performing, so this NAN will help us to handle aggregations. So for that, you have a special universal functions in Numpy called non-safe versions, right? These are the equivalent universal functions for a normal universal functions. These are equivalent non-safe versions of universal functions. This computes nan sum, okay, nan product, and so on. You have every alternate non-safe version universal function for the given universal function. We'll see how we are internally computing different operations to get the summarization of the arrays. In next session, we'll focus on computations on arrays using broadcasting. As I told you, this Numpy universal functions will work on different dimensional arrays when you are applying arithmetic, logical, and other operations, bitwise operations on different dimensional arrays. They raises various size concerns. To handle them, we have a concept called as a broadcasting in Numpy. Thank you. See you in the next session.